But before, let me call your attention for our book exhibition. And so I brought some. I brought something different this time. It's a more biological book, an interspecific competition in birds, and then there's also something about predator-prey with arthropods, which is different from what I will teach today, which today we'll see a lot of Volterra things, and this is discrete time predator-prey, which we won't discuss here because we don't have time for all of this. Okay. And then there's also resource competition and community structure by Tillmans, a classic about competition. And then there are two historical books, this is very nice. It's Modeling Nature. It's the history of population biology. So it's something which it's nice. I mean, it's more like to read and okay, so just. And then there's this book that's very difficult to obtain. I could find it only at a bookstore that sells old books. And this is the Cold Spring Harbor Symposium on Quantitative Biology from 1957. And it's impressive, the list of people that participated in that. You have lots of important people, like people from evolution, like Richard Lewontin, Dobzhansky, Cavalli-Sforza, and also in this symposium, there was a very important presentation by a guy called Nicholson, who is about, there's a model called Nicholson-Bailey, and this is about usually a model used for these guys here, for arthropods or for insects and so on in discrete time. And that was a moment that was clearly put that the regulation of populations is density dependent, right? And the non-linearities, which was contradicted by other guys at the symposium. There's a whole discussion, the transcription of the discussion is also there. Okay? And then there's the most famous paper of this book is called Concluding Remarks. And it's a very, very cited, but paper by Hutchinson, the guy that I always mention with historical things. So this is the concluding remarks, and he outlines the idea of what is a niche, right? So it's of historical importance, and it's nice to take a look and so on. You won't read this book, but concluding remarks is a classical paper that you find easily online, even. Yeah. So, okay. Yesterday we saw competition, and we will on Friday take at least some time to discuss a little bit more about competition, more trying to see where our Volterra model is weak and how we could do something better, which we will do next week. But so that today we will move to predator-prey interactions. Okay, as I told you yesterday, this is a generic name, some kind of umbrella name for antagonistic interactions. So, okay. So again, now we will have two species. Okay, one is the predator, the other is the prey. Right. So I will use the usual notation, which has nothing very important in itself. It's just, which will be N of t will be the prey population, and P of t is the predator. Okay. Some books prefer to use a V here. It's a victim. Yeah, I think Gotelli does. Book of Gotelli is victim. Okay, So, and I have to make some hypothesis about this species in order to build a model. Many kinds of predators and many kinds of prey. So what we will suppose here is that the prey in the absence of the predator and the prey increases exponentially. Right? I'm not. It's obvious that if there should be somehow a carrying capacity, but I don't want to take the carrying capacity into consideration right now. Okay, so let's do it simple. Because I mean it will never go actually to exponential because the prey is there. Okay, so it will be that's a kind of situation where you'd say that this prey is regulated top down. So that's pure top-down regulation. If I put a carrying capacity, I'm saying that there's top-down from the action of the predator, but there's also some bottom-up regulation for the prey, because carrying capacity means that there are not sufficient resources to grow more and more. So what I'm modeling here is it's a top-down regulation of the prey. And I will suppose that the predator is a specialist, meaning that this predator feeds only on that prey. In the absence of that prey, it will decay to zero, the population will die out. Okay? So this is obviously not general, but I mean, if you try to do everything general, we don't do anything. So let's start with this, okay? And so I have to write two equations. And I want to take this hypothesis into the equation, so the prey should grow exponentially in the absence of the predator. Therefore, there should be something like that. Okay? Malthus. Okay? Now, the predator is a specialist in the absence of the prey. It should die out. Okay, so I will put just a term which is minus m p, m for mortality. Okay, so the solution of this is exponentially that goes to zero. Okay, so these are the part which we could call the non-interactions. Okay, we are not taking interaction into account. In order to take the interaction into account, we have to write something on this side. And of this, in this place here, which depends on P, and here's something that depends on N. Okay, so I will use the same things that we have used in the Volterra model for competition. I will use what's called a mass action term. So let us first write it as a constant times N times P. And another constant here times n times p. So let's try to see the meaning of these things, okay? So, well, why I could say, okay, could I have put here just a function of the predator without the n? Okay? Okay, if this would give you what? A lot of predators, and the population going down, and down, and then you get a negative population, because nothing stops. Okay? This doesn't go to negative values because it's an n here. So the idea is that you need both n and p in order to have predator-prey dynamics. Okay? In the absence of prey, if I had put not this n here, in the absence of an initial condition being 0 prey, would give me a negative population of prey, which is inconsistent. Okay, so you need something that maintains positivity of your population. Okay, every time you get some negative population, you better review everything, because it's probably wrong. Okay, in any model. But negative populations it's a problem, unless there is a very specific situation where you can give a meaning for this. But usually negative population is your model has problems. Okay. Okay. So let's still take a look at this, guys, here. So I can also write this in this following way. 1 over n is dn dt is r, which is the intrinsic growth rate without population regulation, like Malthus, minus some c times p. Okay? So now we can think in the following way. Think we have only one guy here. Okay? So this is the per capita growth or decrease, the per capita variation of the population. So C is the per capita variation of the population due to one predator. Okay, if I have one predator, this means it will induce a change in the population, which will decrease the population, and this will give you the variation induced by one predator. Okay, so this is the interpretation for C. Okay. Now I could have written this also in a different way. I could have divided everything by p, and I have dn dt. Then I would have something very weird here. Okay, but I don't want to think about this here now. I just have minus c times n here. Okay, so this says that we are focused on this term. Okay, this is the variation in the population size in time per predator, and it's proportional to the number of prey. So this is a predator that this variation induced by per predator, it's proportional to n. If I have certain consumption, you can think of this as consumption of the prey. If I have a certain level of consumptions per predator with a certain population, say 100 individuals, if I have 200, I have double consummation. Okay, so that's what is behind this guy. Okay, so here the only interesting term would be this one. Okay, and this would say just that this guy here you have a negative and here a positive, so that's different from yesterday. We had two negative signs in front of the coupling terms of the nonlinear terms. Okay, so and here this is kind of B is kind giving you this consumption term, which decreases the number of prey, will increase the number of predators by the same, not the same amount, but in the same n times p, but some different coefficients, which is the conversion coefficient, because it's not that you eat one chicken and you create one person. Okay, you have to eat many chicken in order to create a person. So yeah, these are counting population. So there has to be some conversion. Okay, that this conversion in the C and B will obviously be the dependent on the practical situation of the species that you are considering. Okay. So for real predation, not general antagonistic things, this is usually the C will be called the predation rate. Okay. So and B would be the conversion rate. Okay. So that is what these symbols mean. Now here,
Professor.
we are doing something. Somebody.
Oh, sorry. I understand. Like C is the number of preys that each predator will catch.
C is the number. It's not the number. It's the per capita number.
Yep.
Okay, per capita.
And what is B? The difference.
B is the conversion, because you have this consumption here, and somehow it's creating predators. Okay.
Okay.
So it's creating predators. Sometimes this is written like this, like C times some alpha. But in order, we will. It is almost. I mean, if C were 0, this would have to be 0 also. Yeah. Okay. So, this is decreasing the population of prey which are being consumed in this model, and somehow this has to increase here the population. Okay. So this is the conversion. It's not that you have exact. You could think that everything that goes out from the prey equation goes to the predator, but it's not that you have one prey creates one predator. There's a conversion factor, which in tomorrow we'll call it numerical response. It's more or less obvious, right? It's numerical transformation between predators and prey.
Okay, thanks.
And prey to predators. Yeah. This is different, for instance, what we will see later in the course on epidemiology, where you have a kind of predator-prey dynamics. You have susceptibles and you have infected. So the infected are the predators, and the prey is the infected are the predators, and the susceptibles would be the prey. And then when you have a term that describes the infection, transforming susceptibles to infected, but then it's not. It's the same, exactly the same term. It's not. There's no conversion factor. It's human to human. One person that gets infected, that leaves the susceptible compartment, will be one person in the infected compartment. So it would be perfect conversion. Okay, there are no conversion factor in epidemiology, but for predator prey, yes, we have to have the conversion factor. Okay? So, well. Okay. Can we go on now? But now begins a little bit mathematical analysis of what will be the dynamics which is implied by this. Okay? So let's do it step by step. But I will erase this part here, this discussion. Okay? So
Professor, one doubt. This minus MP, why is negative? Because, I mean, if I have more predators, they will not reproduce and
no,
raise
predators only reproduce because of the existence of the prey. The hypothesis is it's a generalist, and all new predators come from the consumption of the prey. Therefore, I would have, if I wrote something like that, okay, and forget about this one, okay, that's ridiculous, right? You would have birth minus death times m times p, okay? So birth is 0, natural birth is 0. It comes only from the predators, from the prey. Therefore, there is a minus sign. Okay, but I use not d, I use m. Okay, so and this means that the population without the prey will decay exponentially. Okay? So this is important because you can obviously generalize this and put some intrinsic growth rate because it's not not a specialist. It's such did I say generalist at a certain point? Yeah, it's a specialist. Okay, so it's a specialist. If it were a generalist, it would have other resources, and then you could model this by some birth rate. Okay, all of this can be done. We have to choose what we will do first. Okay. Yeah. So, well, what would be your first instinct to look at these equations? Find the fixed points. Okay. We are fixed point finders here. Okay. So let's do it, and then I will show you that maybe it was not the best idea in the world. But anyhow, so the fixed points are defined by dn dt equal to 0, and dp dt equal to 0, the values of n and p, where the population is 0, and this here implies that r times, you have n, I can use n outside here, n times r minus cp, okay? And here I can put p times b n minus m. Okay, so that we need this to be 0. These are simple equations. Then obviously there's the n equal to 0, p equal to 0 fixed point. Okay, which is not very interesting, and unless it's stable. It will be easy to show it's not stable, the fixed point. So the one fixed point is n equal to 0, p equal to 0. Okay. Then you could say, okay, maybe n is equal to 0, but p is equal to something else. But we know that if there are no prey, the predator will die out. Okay, so no point. Okay, and you could say maybe you have just the prey and no predator. P is equal and n increases exponentially. We are not interested. It's not a fixed point. Okay, so this is one point, and the other one is when this here and this here are 0. Therefore, there's the point p equal to r over c, and n equal to m over b. These are the fixed points. Okay? So, only 0 and this fixed point. Yes? So we want to find populations which would be the stability of the system, the stable equilibrium. Okay, we want to find this. Okay, if it exists, we don't know if it exists, but we're trying to find it. Okay, so then I'd say, okay, if the population is stable, this is 0. Okay, and this is also 0. And if this is 0, then the other side of this equation has to be 0. Therefore, I have this equal to 0 and this equal to 0. So how can I solve both of these linear equations at the same time? Well, there's n equal to 0 and p equal to 0, because then you have a 0 here and a 0 here. This is one solution. Then the other solution is this here equal to 0 and this here equal to 0. So therefore p is equal to r over c, and n is equal to m over b. Then this is 0 and this is 0. But yeah, again, both of them satisfied. And this are the only ones, because you could say, maybe n is 0 and p is different from 0. But n is 0 means no prey. And we know that without the prey, the predator will die out. So there is no fixed point there. Okay? And I could say maybe p is equal to 0 and n is something else. But n, in the absence of the predator, grows exponentially. This is not a fixed point. It's just a growth. Okay? So the only two fixed points are this one. Okay? Those. Well, now, okay, let's pay attention. Okay? Rescaling of variables. Again and again, we will do this. Okay? And I will introduce a new variable, u, and a new variable v. U will be the prey population, V will be proportional to predator population. Okay? And I will multiply U by B over M. And V by C over R. Okay? So these are constants. I'm just scaling the population of predators and prey. Okay? It's not a non-dimensionalization because there's no scale for the population size, which would be carrying capacity, but we don't have it. Okay? So we are not interested in, we are just trying to simplify the system, and we are not taking it in a non-dimensional form. Okay? So, now I have to substitute these equations here. What do I get? Well, N is equal to M over B U, okay, du dt. Okay, this first term here will be equal to R times N, which is, I need a mistake here, yeah. Ah, no, okay. Okay. It's B over M. Did I do this correctly? Let's see. Maybe I made a mistake, but let me see. Okay, so yeah, I probably did a mistake. No, okay. That's R times M over B U, which is this term, minus C times N times P. So N is M over B times U, but P is R over C times V. Okay? R over C times V. Okay? Then I can cancel M over B here, M over B here, M over B here, and this C goes with this one, and this goes with this one. Okay? Therefore, I end up with this here, which is RU minus RUV, which is RU1 minus V. Okay? Beautiful. Simple, okay? Simple equation. Yeah. Okay, this is the first equation, and I can add the second equation, which is dp dt. So dp dt will be R over C gv dt will be equal to B times N, which is M over B, times P, which is R over C U times V, here, this term, minus M times P, which is R over C V, which gives you the equation. I can cancel R over C here, R over C here, R over C here, okay? And the B also cancels here. I get the equation dV dt is equal to M times V times U minus 1. Okay, so this is the first term. This is M times U times V, and this is M times V. Okay, okay. So with this nice fixed point is just 1, 1. Okay, so the fixed point, which would be U star, the fixed value, would be 1, and V star would be 1. Okay, very good. So let me write again the system here that we got here, the U dt, where U is the prey. It's R times U1 minus V, and dV dt, it's equal to M times v times 1 minus u. Okay, and the fixed points are these ones. Okay, so now we want to examine the stability of the fixed points. Okay, and we will start with the stability of the 0, 0. Okay, this is the one that we are interested more, but first let us check this other pair of 0, 0. Okay, so near the 0, so stability of the fixed point, I will put 0, 0. Okay, in order to do this, you know that u and v are. How do you study the stability? You go on the fixed point, okay, and make a small perturbation. So you are not on 0, 0, but on very small numbers near 0, 0. So the small numbers means that u times v is still even more, I mean even smaller, okay? It's even smaller. So this term, if you write, you have ru minus ru times v. This term is much smaller than this term. Therefore, I can write that du dt approximately equal to RT, Ru, okay? And the same thing here, dv dt would be what? The nonlinear term can be omitted, okay? So I made a mistake here, sorry. So u minus 1 was not 1 minus u. Okay? So because you have to have a positive nonlinear term and a negative one here. Sorry, okay? And now I use the same thing. I mean, this is m times v times u minus mv. And as u and v are small, because we are near the fixed point 0, 0, this term is two small quantities multiplied are even smaller. Therefore, this is the dominant term. I would have approximately minus v mv. Now, this says that population u will increase and therefore will go away from the point, okay? From the fixed point. Therefore, it's unstable. No matter that this here would be a population of v would go to 0, okay? But the population of p would increase, so it would go away, okay? So, unstable fixed point, okay? The solution of this is u equal to some constant, okay? E to RT, okay? So it's increasing, okay? Therefore, it's not going, if it were decreasing, it would be going back to 0. But it's not going back to 0, it's increasing. Therefore, the fixed point is not stable. I make a small perturbation, introduce a small population of prey and predators, and this term just goes away. Doesn't stay near the 0, 0. It doesn't stay small even, okay? Grows exponentially. This one would give you a decay, some other constant, say k bar, e to minus mt, which should be decaying. But we have to have, that in order to study stability, the idea is that small perturbation, you want to know if it stays close to the, when it goes back to the fixed point or not. And this is not going back, even if you have what people call sometimes that is jargon. That's a stable manifold in this case, but we don't need manifolds for this discussion. Okay, so this is unstable fixing point. So now we want our other fixed point. This one. Well, again, new variables in order to do this easily. So I will define a variable which I will call x, which is u minus 1. and a variable where it's got y, which is v minus 1. And in these variables, the fixed point 1, 1 will be 0, 0 for x and y. Okay? So the fixed point, which I would call x star, is 0, y star is 0, and then I can substitute this here and repeat the analysis around 0, 0, where I can always use that the functions are small. Okay? So if I go for this here, it's the u dt stays the u dt. We'll give you dx dt, sorry. Okay? Then you have r times u, which is x plus 1. Okay? Times 1 minus v, which is minus y. Okay? This is minus y, and the u is x plus 1. That's here. Okay? And the second equation will give you the following. dy dt, because the derivative of v is the same as the derivative of y, because it's just a plus 1, plus minus 1. Here, okay? So you have m times v, and v is y plus 1. Okay? And u minus 1 is just x. So in this new system, the new variables, these are my original equations. We have transformed from the first one, which are the Lotka-Volterra equation. Then we just choose to rescale the populations. And now I just, that's a mathematical trick to make the calculation easy, okay? This part is, there is no big point here. It's just introducing new variables with other old variables minus 1, okay? And now in the x and y, the fixed point u equal to 1 and v equal to 1 is just the fixed point 0, 0. And therefore I can do now the same reasoning I had done before. Where is my and study the stability of the fixed point 0, 0. Okay? In the variables x and y. Okay? So, same reasoning. We can always discard the term that is the multiplication, because y and x are negative, are small, because we are studying their values near 0, 0. Therefore, I have this approximate equation minus ry. Then I get this other equation here, which will give you approximately equal to mx. So now there's a coupled equations, okay? Y is driving x, and x is driving y. Okay, so now it's, however, these are linear equations, and linear equations, and this guy can think this is a system of two first-order linear equations, okay? Yeah, are always easy to solve. So what do? You do what people call in physics an ansatz, which means I will try something, okay? I will try x equal to, let me see, some some constant, e to lambda times t, so an exponential, okay? And y, I will try a different constant, but the same exponential, okay? So this is, here you use this as an ansatz and so on, but you can show for linear equations with constant coefficients that you can always write any solutions in as a combination of exponentials. Okay, so this is, I mean, this is a basic point of theory of differential equations. Do not suppose that you know it, but accept that I will try this, okay, and see what happens. But because this gives me growth rates, okay? Like, is it growing? Or if lambda is positive, it's growing away, the fixed point is unstable. If lambda is negative, the fixed point is stable. Okay, so we want to know the sign of lambda. And let's see. If I do this here, and I input this here, what will I get? I will get dx dt is a e to lambda t minus r times b e to lambda t. Okay? I can cancel the exponentials, and this gives me that, oh, sorry, I forgot the lambda here, okay? The derivative of x is a times lambda e to the lambda t, okay? I forgot the lambda here, okay? And on this side there's no lambda because it's not a derivative, it's just a function. So you'd have lambda equal to r times b over a, okay? But it's still, you don't know the sign because you don't know a and b are just arbitrary constants. There's a minus sign here. There's a minus sign. Okay? Yeah, you are right. There's a minus sign. Okay. Sorry. Very important minus sign. Thank you. Very, very important. Most important minus sign of your life. Now, then here I do the same. I will have lambda times b e to lambda t, which is this term here, and here without any minus sign. M times b e to lambda t, which will give you again some lambda, which will be m times times a over b. Now, I know that a over b can be calculated here, okay? This implies that I can invert this a over b, okay? Will be minus r over lambda, okay? You agree? I put this a here, I put this b here, and I could get the lambda here. It's minus r over lambda. Therefore, you get an equation here. Okay? So this implies, using this one, that lambda is equal to m minus r over lambda. Therefore, lambda squared is minus mr. Surprise, surprise. No real solution. Imaginary numbers. Lambda is equal to plus or minus I times square root of r. So lambda is not positive, it's not negative. The real part is 0. It's 0. Because I induced you to think that lambda is real and it has to be positive or negative, but it could also be 0, yes? And so the real part is 0. And what is imaginary solution in this case? Well, we go back to the solutions and we look at that would be x equal to some constant, which will depend obviously on the initial condition, times e to minus, to plus or minus, I will just use one of them, okay? And I times square root of t. And this is equal to a times sinus of square root of m r times t plus I cosinus of the same thing, okay? Of the same argument. Okay? So I could also have written, we have two of them, and I can take only the real part of this x. And the real part is a sinus. It's oscillating. Okay, it implies that x is oscillating in the same thing for y. Just substitute and do the same thing. So imaginary lambda is called an eigenvalue. Okay? I didn't formulate it in a matrix way, and so that's why I did this change of variables in order not to introduce a linear algebra things, but it's in linear algebra, this lambda is called an eigenvalue. Okay? In Portuguese or in Spanish, autovalor. Okay? And so what can we do with this? Okay? So it turned out that we went for what we thought would be the first thing to do is I find the fixed points and I look at its stability, and it turned out that one fixed point is unstable, the 0, 0, and then the other fixed point, which was the old 1, 1, and okay, this fixed point here, well, it's not written anymore. Okay, this fixed point does not neither go away nor decay. It does not increase, it does not decrease. It oscillates around, okay? Oscillating around the fixed point. So we got oscillations of the population, okay? Population, both of population y and x are oscillating. And so the implication, which we will discuss more, is the Lotka-Volterra model for predator-prey dynamics has oscillating solutions. Actually, they are periodic solutions. Okay? So that's the importance of this model, because this model will be totally criticized in just some moments. Okay? Because it has some features that are not realistic also. But the important point is that it shows that there are mechanisms in nature, a predator-prey relation, which can induce oscillatory behavior. And this comes back to one of the fundamental questions, and when you observe of population biology, and the fundamental question when you observe nature, it's why are the population changing and how? And what are the mechanisms that make them change? Or why are they constant at a certain level? Okay? So this says that there's a mechanism in nature, the predator-prey dynamics, that can induce oscillations. Okay? Because there are other mechanisms. There are mechanisms that we saw with the non-overlapping generations. We had also oscillations. Okay? But there were no predator-prey at all at this point. And then you have oscillation induced by variability of the environment, like the seasons or the days, which has no predator-prey. It's not even connected to interactions. Okay? So this says here essentially that predator-prey dynamics has a mechanism to create oscillations. Now, we want to do something else. So let's try to look again at our system of equations, which I will erase this part, but I will leave the system U and V, okay? Which we now know that the perturbations around U and V should be oscillating, okay? And the fixed point, around the fixed point, 1, 1, okay? So, okay, I will leave behind the calculations, okay? We don't want the x and y. This was just a trick in order to make the stability analysis more easier. So once we get the result, we throw them away. Okay? So let's make a plot where I will put the predator here and the prey here. Same thing that we did yesterday. Yesterday they had all these null clients, okay? But in this case here we have the null clients are very easy. I mean, it's just if I want the null client for u, it's just the v equal to 1, okay? So it's this line, okay? And the null client for v is when this is equal to 0, and this is just the line u equal to 1, okay? So this is 1, and this is 1. You have the interception where you have the fixed point, which one is neutrally stable, right? That's the third case. You have unstable, stable, and this is neutral stability. It's now, let us again think about. Let us think what happens in each of these quadrants. Okay, each of them. Here, in this quadrant, when we are near 0, 0, okay, we know that in this part here, this function v will be increasing, and the function u will also be increasing because it's near the 0. Okay, so u has this tendency, and v has this tendency. Okay. Now, if I cross this here, okay, I will revert the sign of v. Okay? So, reverting the sign of v, you will have this and this, not inverted. Okay? And if I cross again, I will have this, and let me like this. And if I cross here, looking at the null clients and so on, what you will get is something that is still increasing here and decreasing here. So you can see that if you start here, you are going somewhere here, and then you go 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 here. Okay? So now I'm doing something which is a little bit you should protest, because I'm saying that there's a circle, okay, but nothing what we did actually showed that the oscillations will close on there could be circles which never, I mean, that would not be a closed circle, could be something like this, okay? Oscillations like this, okay? Could be. So I'm drawing one that's just really a circle or ellipse or whatever, okay? Yeah.
When u and v are smaller than 1, when u and v are smaller than 1, the v should be decreasing, no?
V is decreasing. More than 1? Yeah. Here, in this part, v is decreasing.
No, but when they are smaller than 1, in this quadrant below, in the left.
Here?
Yeah.
V is increasing?
No, but it should be decreasing, no?
I think that, but it didn't. Ah, yeah, you're right. I made the wrong null clients. I changed it to null clients. Okay, let's do it again. Okay, thank you. Okay, this one has to go here, like this. Okay? And when I cross this one, v equal to 1 will be the null cline of u. No, if I cross this one, if I cross this one, I will have something. No, it's not working well. Why is it not? There's something. I think I inverted the axis. Yeah, sorry. So this is U, this is the prey. Okay. This is the prey, and the prey increases here. Okay, that's true because near the V, and the predator, which is V, decreases. That's correct. Now, if I go to this point, where U is still small, okay, then this continues to be small, U, then it will go this way, but this goes this way. It's something is not correct here. I don't know why. I made some mistake. Okay, that's the null line for U. No, that's the null line for U. Therefore, this thing should be that this way, but it's not not correct.
I think it is correct. If you put all the directions and like see a point, it will make a circle. It's just that it's unintrusive. No. Arrow from the left.
Now, okay, this one. Okay, now I have to change the direction of this one. Okay, from here to here, I change the direction of V. Okay, and it should be like this. Okay, and here I would have changed both. Yes, like this. One. Okay, now let me see if we have a circle. When you go here, and this way, you go here. Okay, then here and here. Okay, it's again a circle. Thank you. I was creating having changed the U per V, the circle would be corresponding to prey consuming predators instead of predators consuming prey. Okay? So, thank you. Sorry for the thing. So, okay, so there are circles, but can we do something else? So, first, we don't know if there are circles, okay? They are oscillating, okay? But we don't know if it's periodic. Oscillation is something. Periodic means that the system goes from one point, and after some time, after the period, it goes to the same point. The point in the plane are populations of prey and predators, okay? So it has to go back to the same one to be a periodic one. So for the time being, we have not shown the periodic one. We have shown that there are oscillations. Okay. So first we found oscillations near this here. Okay, near the fixed point, which were sinus and cosinus. Okay. Now with this analysis, we have found that we expect something like oscillations on the whole plane, not only here, because we had first shown only here. Okay? Now, near the fixed point. Now, even away from the fixed point, you have oscillatory behavior. Now, well, in order to proceed, you will need to do some analysis. Okay? So, you look at that here. And now, for the horror of mathematicians, but not so horror because it is actually correct, you can divide one equation by the other. Right? Therefore, I will get du dv. Okay? Eliminating time. But I mean, that's actually correct because these are regular expressions. Okay? There are no singularities that you cannot go in back and forth. Okay? So you divide one by the other, and time disappears, and therefore I have only the dynamics on the uv, which is this plane here. Okay, I have it only here, and then I get this r times u 1 minus v times m v u minus 1. Okay, now I need to do an integration. So if you are not very comfortable with the integrations and the manipulation with the equations, in 5 minutes it's over, and you can come back to the discussion, okay? So, in the mathematical jargon, this is a separable equation, which is separable. Separable is that I can write it this way. du is over, let me see the best way, it's times m. I could put the m here, du here, over times u minus 1 divided by u is equal to r times dv times 1 minus v divided by v. Okay? So just throwing around. This guy goes here, this one goes here, this one stays, this stays, and dv goes here, and the du gets here. Okay? So this is only a function of u, and this is only a function of v. So that means separability. And this means that if I now take the integral of both parts, okay, I can take the integral because I can know this thing. So this is, if I take the integral, okay, let him be here. Okay, I will have m times du. Okay, here u over u is 1 minus 1 over u. And I take the integral. Will be equal to r gv times 1 over v minus 1. Okay? Plus constants. Okay? Can always add a constant. When you do integration, you can always add a constant. Okay? This is important here. But now this thing you know how to solve. This is just m times u minus, okay, let's put the m here, minus logarithm of u. Okay? So this is equal to r times logarithm of v minus v plus some constant. Okay? So we started with a differential equation. And we have not solved the differential equation, but we have found that there's a relation between u and v. There's no differential equation anymore here. Okay? No derivatives. So we integrated out everything. So this here is what physicists call a conservation law. The motion in the uv plane has to be such that this thing is fulfied. Or if you want, you can write this like this: mu minus n minus r, or just plus r if you want, v minus n v, okay, is equal to some constant. Okay, therefore the motion in this plane, when I start here, it has to be such a curve that this here is fulfied. Now, what is k? How do you calculate k? So you have to give initial conditions. Okay, I have to give at the time t equal to 0. I have to give the initial conditions. Therefore, if I give the initial conditions, u is equal to some u0 and v is equal to some v0, I calculate k here. Okay, so k comes from the initial conditions. Okay, so everything is okay. I have the differential equation. I have this plane. I have this other differential equation. I give the initial conditions, and I have a curve here. Now, this thing here is the conservation equation. But it's like this quantity is like conserved. Okay, but well, it doesn't have any interpretation. Okay, well, a little bit interpretation it has, but you have to go to theory of parabolic equations as a kind of entropy. But never mind. Okay, so now you can say the following. That's like when you have, for instance, the equation of a circle. Okay, you have x and y. Then you look what the points on your plane, such that you have x square plus y square equal to the radius square. Okay, so now you can also do this with this instead of the circle. So there you will look for the geometrical locus of the curves that satisfy this. And this you cannot do this. I mean, you can do a weird exercise of trying to draw these things, okay? But you're at put it on a computer, okay? It's easier. Okay, so because of this conservation law, because of this, we will be able to draw the trajectories of the system. Here's the 1, okay? And the trajectories, if you look at this here, okay, will be something like this. Very bad drawing. Why are there so many? Each of these ones correspond to a certain value of k. If I start here, okay, I give the initial conditions, I have a certain value of k, and I draw the lines, and you get this, and it's a closed line. Okay? You could try to show this analytically also. Okay. If you have a different initial conditions, you are here, and you circle again. So for each initial condition, I have a circle, and I have an oscillation, which is not sinus and cosinus, because it's, you know, it's something like this. And if you would go and solve numerically for u and for v, okay, you would have things. So v is what was it? V is the predator, yeah? Okay. Yeah. Okay. So u is the prey. So you would have oscillations, but not oscillations which are symmetric. So they would have something like this. Okay. And here, if this is the predator, it will also do this, but a little bit in later. Okay. So, so these are oscillations. In a periodic, you start here, you get back to this point here. Okay. So they are periodic, but they are not circles. They are not sinus and cosinus. Okay, they are deformed things, right? Because you have to. I mean, this equation preserves the positivity of the first quadrant. Therefore, you cannot have. If you start here, you cannot oscillate like a sinus. You go to negative. Okay. So let's see if this makes some sense. So this is. If I put u here and v here, okay, this is the prey, and this is the predator. Okay, let's say we start here. Okay, just yeah.
Yes, in these graphs, the x-axis is the time.
Yeah. It's the. I'm not very good with axes today. Okay. Now, this one, let's say start here. If you start here, you go this way, means the prey is increasing, u is increasing, okay? But also v is increasing, yeah? You are going this way and up. Therefore, u is increasing, v is increasing. When you get to this point here, prey was increasing, and now it's not anymore increasing. It will go decreasing. But predators are still increasing. But then, when you go up here, what you get? You get that at a certain point here, the number of prey, u, is pretty much smaller, because you went this way, and the predator starts to decrease because there's not enough food, not enough prey. So here is another point, then the predator decays and the prey is still decays, but as the predator is depleted, the number of predators is small, the number of prey starts to grow again. And then it comes to this point, then the predators can grow again. So first you have growth of prey, then the predator grows, the predator depletes the number of prey to such a point that the predator itself will start to decrease because there are no prey. But as the predator decreases, the pressure of predation upon the prey decreases, the prey can grow again. And then it grows again. After some time, the predator will again grow, and then everything repeats itself. So it's periodic, and what's behind is this mechanisms, okay, which are the mechanisms that show the oscillations and which correspond to this dynamics. Okay, prey, it's increasing, then consequently the predator increases also, and then it starts to deplete the population of prey. Then there's not enough resources. The predator starts to decrease, then the resources, the prey grows again, and so on. Okay. Now this is the main result of the Lotka-Volterra model. We have oscillations. They are not what people in physics and math call harmonic oscillation. And harmonic is sinus and cosinus, things that go regularly. Okay, they are pretty deformed. Maybe on Friday I can show you the exact solution. Okay, exact in the sense that the plot. We cannot find the exact solution in terms of analytical expressions. Okay, so you have this thing. Okay, now this is the glory of the model, that is has been motivated by a real practical problem. Okay, that is the story of Volterra, and there was a very important person that in the city of Ancona in Italy, and they had there was one guy, this is Umberto d'Ancona, who was, I don't know what he was exactly, but he was managing fisheries. Okay, so management of fisheries, and they had very weird oscillations. Why are there here certain species, which I can't remember now exactly, disappears, or it's at very low stocks, and then in other years it's growing. Then why are the fish stocks oscillating? Was kind of, and it was not a annual oscillation, because annual would say has to do with the temperature or whatever, okay? But no, didn't. Was some like not even multiple of years, but 3 years and a half, something like very weird. And well, I don't know. It was an acquaintance of Volterra, and Volterra then came out with this solution, because the population of small sharks also oscillated. The sharks were the predators, okay? And the other one, the prey of the shark, he came out with the solution, okay? And that was celebrated at the time, okay? So the Lotka-Volterra equation. So glory. Now, what's the problem with this equation? Let's destroy the equation. Okay? Well, there are many problems, okay? And the first one that is, well, okay, you could say there should be more biology in the sense that maybe we should have taken into account biological mechanisms that we don't have. For instance, a carrying capacity, or sometimes something else like a generalist predator, or many other things, okay? In the nature, things are not two species, there are many interactions and so on. But okay, but we want to have, I want to show you one problem, which is a kind of mathematical problem, which makes this equation non-applicable to real situations. This is the following, okay? Now, you have all the circles, okay? And I start here, okay? At a certain initial condition, and then I would circle here. But this system is not isolated of the world. It's perturbed, okay? If these are predator-preys in the nature, it could rain, it could be forest fires, many things happen over the life of a predator and a prey. It depends on the exact circumstances, the sizes and so on, but there is no such thing that has no noise. Environmental noise, okay? Environment changes. So you are here, and then suddenly there's a change and you go here. Woof, artificial, because something happened, okay? And then you will circle here, okay? And then maybe you got here, and then you got here, and then you get here, and then you get maybe here, and then you get here, okay? Due to perturbations, okay? So this, I didn't say this, but each of this has a period. It's not the same period for all of them. Each has a period, different period. This one has a period, this has a different period, and this has different period. Therefore, under perturbations, you start with a certain speed of the oscillation. Then maybe you slow down, or you increase, and then nothing says that this will actually close here, because you can end up in this inner part, and well, maybe it's not. It does happen that there is no great perturbation, and then it will stay here, and when I get back here, okay. So this says that under perturbations, you want to see the periodic oscillations, because under perturbations this is non-observable. That's called mathematically, this system is not structurally stable. Okay? So Joshua commented on this in the very first lecture, okay? That blood cavitara is not structurally stable. So being non-structurally stable means this. Under perturbations, whatever, you never will see this thing, okay? So this is the misery. We started out, let's see, they started out with a simple model for predator-prey dynamics, and it turned out that we found oscillations, which is the nice part. And then we came to the conclusion that even if you have some kind of oscillatory behavior, you may not see this behavior in these equations, okay, because of the problem of structural stability and instability, okay. So then the question comes is, can we save something? I mean, are we just lost again and we have no theory at all, or will there something remain, okay? So the answer is yes, and that will be the topic of the next class tomorrow, which is more modern theory about predator-prey dynamics, which is everything we did here is correct mathematically, but we have made the assumption of specialist predators and a prey that can increase exponentially in the absence of predators, and maybe we should modify something, okay? So what can we modify? One thing is obvious: put some carrying capacity for the prey, okay? Then the question will be, do I still have oscillations or not? So the answer tomorrow, okay? But then you can also say, okay, maybe we have taken a specialist, but let's stay with the specialist. Yeah? But remember, I showed you the quantity of prey that is consumed by one predator is proportional to the number of prey. Remember that, okay, when we formulated it at the beginning of the class. So if I have 100 prey, if I have 100 prey, that will generate a certain amount of predators through the equations, then you will have, if you have 200, then you have twice, okay? So, and the number of prey being consumed is also proportional to the number of prey, okay? That's what in some equation, where are the equations? Okay, I have, well, they are non-dimensional, but anyhow, you remember that, okay? That the number of prey being consumed by one predator is proportional to the number of prey. Therefore, I have a predator. Say I am a predator, and I've given a prey, like, let's say my prey is hamburgers, okay? Give me 2 hamburgers, and I will eat it, okay? And, but if you give me 10, I will eat it in the same time. And if you give me 1,000, I eat the 1,000. And this is obviously not true. So there is something which is connected to the fact that I have, for instance, to manipulate the prey. The hamburger, I have to open it, and then it takes time. Okay? And then in nature also predators have to manipulate the prey in order to consume it. And also they get, after consuming one prey, maybe they won't consume the next prey in the same time, because it's not there's some kind of regulation that they have to digestion and so on and so on, and then they go to prey again, to look for prey again. Okay? So the idea that the number of prey which is being consumed is just proportional to the number of prey has to go away somehow, okay? Because it's not, it's a super predator. That's some predator that can eat as much as there are prey, okay? So we should modify this equation and introduce something which has to be a characteristic time of manipulation, okay? Or some characteristic time after connected to the satiation, okay? Satiation is not taken into account here, okay? So this is something that we will look in the next class, and this will be less mathematics. I mean, there will be obviously the equations. There are always equations, but we won't be doing all the calculations. But this is long calculations, longer. I mean, equations will have a lot of complicated things which can be done by hand, but you don't want to do it. I don't want it. You should not. Because you can do it computationally much easier. Just plot this kind of thing here on the computer, and then you're done, okay? And so I will just show you the results, but this will introduce you to the modern debates about the nature of predation and the predator-prey dynamics in present time kind of work that's been done now, okay? So today I had 5 minutes, but I don't have anything more to say. So if you have any questions, then I mean they are welcome. Otherwise, we finish here. Okay. So okay, no questions. It was either so clear that no one has any doubt, or it was so confusing that no one understands anything and cannot even pose a question. Okay. But I hope it's not the second option. Okay, thank you.